This research paper, titled Machine Learning for Healthcare Contextual: Improving Clinical Text Summarization in LLMs with Context-Preserving Token Filtering and Knowledge Graphs, is authored by Famida Liza Pia and Rahmatullah Beheshti from the University of Delaware. It focuses on enhancing how we handle unstructured clinical data, like notes in electronic health records, to make them more useful for doctors and researchers. Unstructured clinical data, such as discharge summaries and progress notes, is a treasure trove of information, but it's often messy and hard to sift through. This data includes complex medical terms, subtle hints about a patient's condition, and interconnected details that can influence decisions in patient care. The challenge is to summarize this information effectively, so healthcare professionals can quickly access the most important parts without getting bogged down by irrelevant details. The authors point out that previous studies on clinical text summarization have limitations. Many approaches treat all the words or tokens in the text the same way, which means they might overlook key clinical nuances. Others use simple rule-based filters that don't always capture what's truly critical for medical decision-making. This can lead to summaries that are either too vague or miss important context, potentially affecting patient outcomes. To address these issues, the paper introduces a new framework called ConTextual. This framework combines two main innovations: a context-preserving token filtering method and a domain-specific knowledge graph. Let's break that down. First, the context-preserving token filtering method is designed to identify and keep only the most relevant tokens. Think of tokens as individual words or phrases in the clinical text. Unlike basic filters, this one is smart about maintaining the original context. For example, it might prioritize words that indicate symptoms, diagnoses, or treatments while filtering out redundant or less important details. This helps in creating summaries that are more accurate and coherent. Second, the domain-specific knowledge graph comes into play to enrich the filtered tokens. A knowledge graph is like a structured web of information, tailored here to medical knowledge. It connects concepts, such as linking a symptom to related diseases or medications, based on established medical data. By integrating this graph, ConTextual adds depth to the summaries, making them not just shorter but also more informative and clinically reliable. Together, these elements improve both the linguistic coherence, meaning the summary reads naturally, and the clinical fidelity, ensuring the information is precise and trustworthy for real-world use. The paper discusses how this approach builds on recent advancements in large language models, or LLMs, like GPT-4, Llama 3, and domain-specific ones such as Unstructured or Biomed-LM. These models are great at processing language, but they struggle with the verbosity and jargon in clinical notes, which can make them computationally intensive and less effective. ConTextual aims to make LLMs more efficient by reducing the amount of data they need to process while preserving essential details. In the introduction, the authors emphasize the role of electronic health records, or EHRs, in modern healthcare. EHRs contain both structured data, like lab results, and unstructured data, like narrative notes. While structured data is easy to analyze, unstructured data holds deeper insights but is harder to handle due to its complexity. They reference studies showing that better summarization can lead to improved patient care, highlighting the need for tools that are both accurate and scalable. The framework also addresses practical challenges, such as the high computational demands of fine-tuning LLMs for medical use. Techniques like model pruning, quantization, and distillation are mentioned as ways to optimize these models, making them faster and less resource-heavy. ConTextual fits into this by offering a way to pre-process clinical text before feeding it into an LLM, which reduces the load and improves outcomes. To test ConTextual, the authors conducted extensive evaluations on two public benchmark datasets. These datasets likely include real clinical notes, and the results show that ConTextual outperforms other baseline methods. For instance, it produces summaries that are more precise in terms of clinical accuracy and better at maintaining the original context. This is measured through metrics that assess things like relevance, coherence, and fidelity to the source material. The paper underscores the complementary roles of token-level filtering and knowledge graphs. By filtering tokens first, you streamline the input, and by using the knowledge graph, you enhance the output with structured knowledge. This combination not only boosts the quality of summaries but also makes the process scalable for large-scale healthcare applications. In broader terms, this work highlights how integrating AI techniques with domain-specific knowledge can bridge the gap between general language models and specialized fields like healthcare. It offers a pathway to more efficient clinical workflows, where doctors can get quick, reliable summaries to support timely decision-making. The authors make their code publicly available, which encourages further research and adoption. Overall, ConTextual represents a step forward in making AI more practical and effective for real-world medical challenges, potentially leading to better patient outcomes through optimized information handling.